Okay, I'm recording this without my fancy microphone, so hopefully this will still work. Okay, so this may not exactly be in line with the contingency from 3, but basically going to start talking about probability in general. The contingency tables are based on probability and kind of more directly calculated than distributions like normal distribution. So probability, first of all, is it deals with experiments that yield short-term results, and then you predict long-term. So what would happen over the long term is the probability. So what that means is, like, if I roll a die 6 times, I may roll a 3 once, or I may roll it twice. I'm not very likely to roll it 3 or more. We'll deal with that later. But if I were to roll it 6 million times, the percent of the time that I rolled a 3 would get closer and closer and closer to 16 and 2/3%. So the law of large numbers says as you do it many, 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 many times, then the true probability starts to take hold percentage-wise. So obviously if I roll it a billion times, then I'm going to be off by more than 6 on some given number. So it's a bigger whole number difference, but the percentage error goes to 0 as we go out to infinitely many experiments. The sample space is just a list of all the outcomes. So sometimes it helps to list all the outcomes. When you're doing something theoretical, you guys have been dealing with data that you get from something, but understanding the background of the probability I think would help you, because you sort of understanding the background helps you decide what the numbers mean and how to use them. Okay, an event is some collection of those outcomes. So if your sample space is 1, 2, 3, 4, 5, 6, because you're rolling a die, then a regular 6-sided die, then an event could be rolling even number. An event could be rolling a 3. It could be rolling a prime. It's just something that's a subset of that sample. For any event, E, the probability is between 0 and 1. That's true for any event, any specific outcome, anything. Probability has to be between 0 and 1. An impossible event has probability 0. This we've already talked about. An event certain to occur has probability 1. The sum of the probabilities of all outcomes has to equal 1. So if you add up all the possible results, it has to equal 1. If something has a probability of less than 5%, then it's considered unusual, rare, unlikely. Okay, so a probability model is where you list all the outcomes and you list out all their probabilities. If these don't add up to 1, you have a problem. So we did this before where it wasn't a probability, it was a percentage. But then it really was a probability if you were to do the experiment again. But anyway, this is like in your previous problem set, and you had 1 missing, and the way you found it out was to figure out how they added up to 1, and because it was in percentage terms, that meant adding up to 100. Okay, so if you have the empirical approach, which is I have a die, I think somebody lied to me and it's weighted, and so I'm going to roll it to see how often I roll a 3. Then the probability, the empirical probability of the event, is the number of times the event occurs divided by the number of trials. So if I roll it 60 times and I get a 3 12 times, then 12 over 60. Okay, so here's an example. Okay, so we have 5,000 college students and 150 are math majors. If a student is randomly selected, and when we say randomly selected, that the word random doesn't mean a different question. I'm trying to make this where it's not a response to things you guys have said because I want to use this video in the future, not have to redo it every year. So the word randomly isn't the key to what the denominator is. Randomly means I didn't select in any way that would make me more likely to choose a math major. Okay, so what is the probability that the student is a math major? So that probability is just 150, the number of math majors, divided by 5,000. If they had said, if the student is selected from the College of Arts and Sciences, then we would need to know the number of the College of Arts and Sciences. So this is similar to that seminar I had and will have in all future years, talking about what's on the top and what's on the bottom. Okay, so we put the number of math majors on the top and the number in the population we're looking in on the bottom. And then you reduce it, so it's 350s, that's got 150s. Okay, and if you're asked for a decimal, then it's going to be 0.03. Okay, in a movie theater, in a movie theater, 50 people have popcorn, 35 people do not. What is the probability that a randomly selected person has popcorn? So, the number of people who have popcorn divided by the total number of people. If you were to write 35 here, you ought to be clear right away. That's bigger than 1, so something's wrong. Well, I've got 50 people with popcorn and 35 without popcorn, so altogether I have 85 people. So you have to put all the people down there. So 10 over 17. Okay, the Centers for Disease Control and Prevention reports that in 2002, there were that many boys and that many girls. So we want to approximate the probability that a newborn baby is a boy. So we take the number of boys divided by the total number of babies. Okay, and then that equals whatever it equals. And so because it says approximate, that would mean that you would put this in a calculator and then see to probably 3 decimal places if you were doing it in on-ramps. So you just put this sum in and then this one divided by this. Okay, so now the classical method is the theoretical method. So in this case, instead of counting the number of times you rolled a 3 and dividing by the number of times you rolled, you count the number of ways an event can occur. So in the case of rolling a 3, there's the roll a 3 way, so that's just 1, divided by the number of outcomes. And in the case of a 6-sided die, that's 6. So this is where you get the 1/6. This is the probability you expect to occur if you roll the die long enough. Okay, we have a multiple choice test with 5 choices per problem. So the probability that you guess correctly. Well, there's 1 correct answer. There are 5 choices. So there's a 1/5 of a chance that you're going to get this right. So now we have 2 dice rolled. This is a very standard kind of graph that people draw for the dice, because if you just list out 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the problem is that there's only 1 way to roll a 2. There are 2 ways to roll a 3, so it's twice as likely. There are 3 ways to roll a 4, so that's 3 times as likely as a 2 and 1.5 times as likely as a 3. If you list them out and treat them equally likely, you'll get the probabilities wrong. So this is a chart, and usually when I draw it, because I can't kind of shade things in and make things bold, I draw a pip there, 2 pips there, 3 there, 4, 5, 6, because otherwise you'll end up counting these. So when you count sixes, you'll count these corners if you're not careful. So the probability of getting a sum of 9, 1, 2, 3, 4 nines, 36 squares. So 4 nines, 36 squares. The probability of getting a sum of 7, 1, 2, 3, 4, 5, 6, 6 out of 36, and then you reduce. Now here's a roulette wheel. A roulette wheel has the numbers from 1 to 36, and those are the red and black ones. And then they have 2 green ones, 0 and 00. This is why when you bet roulette on red, it pays even money. They are going to win in the end, but the way they win is because those 2 greens. You don't really have half a chance to get a red. Okay, so we're going to bet odd. So 2, 1, 3, 5, and so forth. The number of odds is 18. You could count them, or you can say 36 divided by 2, because 1 through 36 has half odds and half evens. So there are 18 odds, and there are 38 slots. So the probability you win, you have 18 ways to win, 38 possible outcomes. The probability you lose, whoops, too many fingers there. Okay, the probability that you lose, well, you have the 18 evens plus the 0 plus the 0, 0. There are 20 ways to lose. Okay, so we're picking a person at random, so just human beings. Calculate the probability that his or her birthday is September 26th. We could not do this empirically because we would have to know the people who have birthdays on September 26th and divide by the total number of people. But that's not what we're doing. We're just saying, let's assume that every day has the same chance of having a baby born on it. I think that's probably not true, but let's assume so for the moment. So the number of ways for a person to be born on September 26th is the be born on September 26th way. And there are 365 days. It's really 365.25. So if we were being kind of anal, we'd multiply by 4 up here and 4 down there. Usually when they're calculating probabilities, they act like there are 360 days in a year anyway. But that's what they do in finance math too, just to treat every month like 30 days. We'll get into it later with finance math. It ends up not really making a difference because you use it once to make things small and use it once to make things big. So if you do both those things in the same way, it doesn't hurt. But I'm off on a tangent and we need to keep going with this. Okay, the probability that someone's birthday is in December. So you might just say, well, there's December and there are 12 months. And usually that's going to be pretty close anyway. But December has 31 days. So you might go ahead and do it like this too. It's still very close. Okay, so we talked about tree diagrams. So we're going to flip a coin twice, and we want the probability that we get tails, tails. So when I first flip the coin, I can either get heads or tails. Flip it again, I can either get heads or tails. So this is the only branch that has both tails. And each branch is equally likely because the heads and tails were equally likely. So half, 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 like that. So there's one branch that's tails, tails, out of 4 total branches. So the probability is 1/4. A couple has 3 children. we want the probability that they have exactly 2 boys. And then we want to know if that's unusual. Unusual would be, remember, less than 5%. So that gets them 2 children. Now they need that last child. Okay, so we want to look at the branches that have, it was exactly 2 boys, right? Yes, exactly 2 boys. So if I'm going to have 2 boys, I need to have a girl at the end. If I'm going to start out boy-girl, then I need to have a boy. If I'm going to start out girl, I've got to go boy-boy now to get to. So you don't have to think about it the way I do, obviously. You can just look at the branches and say yes, no, kind of thing. If you go down this branch, you get girl, girl, boy. That's not 2 boys, girl, boy, girl, and so forth. So 3 of them have exactly 2 boys. And they're 1, 2, 3, 4, 5, 6, 7, 8. And this is 0.375, which is way bigger than 0.05, so it's certainly not unusual. It's in fact extremely common. Almost half the time this would happen. Okay, so we're going to assume that both parents have brown-blue eye color genes. And we're going to do the thing where you get one gene from one and the other gene from the other, and what are all the combinations, okay? And then we want to know the probability they have blue eyes and the probability they have brown eyes. If they have any brown genes, they're going to get the brown eyes. So this is the only way to get blue eyes, because if you have the big B, you get brown eyes. So the probability of blue is just 1 out of the 4 possibilities. 3 times you'll get brown eyes. Okay, so a Venn diagram, which I think you've seen before, this is a Venn diagram of 2 things which are mutually exclusive. This circle doesn't touch this circle at all. So they are disjoint and also in finite situations mutually exclusive. That means the same thing. So if you want to know the probability of one or the other, you just add them. Probability works like area. So if I wanted to know the probability of this circle and this circle as a region put together, I would just add them, the 2 circles. So that's the first kind of rule. The probability of E or F, which is written like this, union, that's if E and F are mutually exclusive. Which means they have nothing in common. Okay. So we have a single card drawn from a deck of cards. Here's a picture of a deck of cards. These are called kinds. Ace, 2, 3, 4, 5, 6, and so forth are called kinds. Jacks, queens, and kings are called base cards. And each of these is called a suit. So you have clubs, spades, hearts, diamonds, and each of those is a suit. Okay, so the first question is, what's the probability of a 10? So we count the 10s, 1, 2, 3, 4, and there are 52 cards. So probability of a 10, 4 10s, 52 cards. The probability of a 5 or a 10? Well, there are 4 5s and 4 10s, so 5 or a 10, there are 8 of them. But by the rule we just had, because it's mutually exclusive, which is to say I can't draw both a 5 and a 10 if I draw a single card, then I can just do the probability of 5 or 10 that's the probability of a 5 plus the probability of a 10. And if you're thinking to yourself, it's a whole lot easier just to note that there are 8 of those things. That's true now, but if the situation were more complicated, you need to know these rules so that you can apply the rules when it's not as obvious how many of something there is. A 5 or a 10 or an ace. Again, I can't draw a 5 and an ace or a 10 and an ace or a 5 and a 10. So these are all mutually exclusive. So the probability 5 or 10 or ace is the probability of 5 plus the probability of 10 plus the probability of ace. The other benefit to doing this with this type of stuff is that you can see that it's true. You can see why it's true. You know that these 4s are just adding up the number of 5s and 10s and aces, so that altogether this is the number of cards that fit this. The reason they have to be mutually exclusive is, let's say I said the probability of 5 or king or hearts, then when I counted up the number of 5s, I would have included the 5 of hearts and the 10 of hearts when I counted the 10s. Okay? So a bag contains 5 red marbles, 3 blue marbles, and 2 yellow marbles. You're going to reach in and you're going to select a marble. So we want to calculate the probability that the marble is red or blue. So you could say 1, 2, 3, 4, 5, 6, 7, 8 out of 10. Or you could say the probability of red or blue is the probability of red plus the probability of blue, because we don't have any marbles, which are both. So this is because there are 5 red marbles and 10 marbles. There are 3 blue marbles and 10 marbles. The probability of blue or yellow three blues, 10 marbles. 2 yellows, 10 marbles. Okay, so in a Venn diagram, the intersection is this bit here, and I'll color that in a minute. So it's E and F, which is also the upside down U. An intersection, it works like the intersection of a road, which I've probably mentioned previously to you. If you're in the intersection of Alma and Park, then you're on both Alma and Park. So the intersection is where you're on both. The union is where you're on either. Okay, so it looks like this. This is the intersection. That's the union. This is usually indicated by the word or. This is usually indicated by the word and. Giving you a moment to get this down. Of course, you can always pause the video if you don't have it yet. So if we're trying to find the probability that one thing or another thing occurs, we find the total number of ways that E can occur, the number of ways that F can occur, and then you have to make sure you didn't count anything twice. So if this is E, and this is F. Oh. Here's what happens. So I go through and I count E. And then here's F. And you can see what's happened is that everything in here has been counted twice. So if I subtract it once, then I'm back to just the total. So I just undo the peak counting by subtracting the intersection, because that's what got counted twice. So I take the probability of E or F, I take the probability of E, and I add the probability of F, but then, oops, I counted it twice on the intersection. So I subtract that part. Okay, so we have 30 students, and we have 18 who build birdhouses, 8 who build mailboxes, 3 who build both, that was the wrong thing. And we want the probability of bird or mailbox, birdhouse or mailbox. The easiest thing to do if you have the intersection is always start with the intersection. So we have 3 who build both, so I'm going to go ahead and put that 3. If you have it, put it first, because then I can say, well, 8 build mailboxes, but I already have 3 here. So there's only 5 over there because I need this all to be 8. I have 18 who build birdhouses, but 3 are there, so 15 goes here. There are 30 students in the class. I count 23 in here, so there must be 7 out here who didn't do either of these things. And we wanted the probability of birdhouse or mailbox. That was weird of me. Okay, so 23 were in there, 30 are in the class. So the probability of a birdhouse or a mailbox is 23 over 30. A single card is drawn from a deck of cards, and we want the following probabilities. So the first is the probability of a jack or a red card. Maybe you remember, if not, look on the notes, which are available for you to download. Half of them are red, okay? So the number of jacks is 4. The number of reds is 26. But there are 2 red jacks. There's the jack of hearts and the jack of diamonds. So we have to subtract those jacks because there are 2 of these 4 and 2 of these 26. Probability of a diamond or an ace. So the total number of diamonds is 13. The total number of aces is 4. And remember, I'm always dividing by 52 because that's how many cards there are. The ace of diamonds is the only one that's both, so there's only one of those. Okay, so I'm going to get us right to contingency table, and then I'm going to do that one tomorrow. That's what we're really trying to get at, but again, I'm trying to build you some background here. Because everything adds up to 1, you can have the complement, which means the opposite. So if your event is the probability that someone has a poodle, then the complement is all people who don't have poodles. So the probability of E complement and the probability of E have to add up to 1 because they represent the whole world, because they're just E and not E, and everything's either E or not E. So it adds up to 1. So you take 1 minus, and we've done kind of some of this with the normal curve, so you're a little familiar. According to National Gambling Impact Study Commission, 52% of Americans have played state lotteries. So what is the probability that a randomly selected American has not played a state lottery? Well, 48%, because it's the other people, the ones who haven't. The ones who have are 52%, the ones who haven't are 48%. In a survey of 500 randomly selected high school students, 420 played organized sports. So we want to know the probability a randomly selected student did not play organized sports. And then, is it unusual? So the probability that you play is 420 out of 500. The probability that you do not play is therefore 1 minus 21 over 25, which is 4 over 25, pardon my scribble. That's 0.16 greater than 0.05. Not unusual. Okay, so I'm going to stop this one here, and I will film the next one in the morning while you guys are having project time.